All right, so today we plan on covering two more things. I want to cover one thing called the variance, which is related to expected value expectation. And I also want to cover one more discrete random variable, which is very important, called the Poisson random variable. So before we do the Poisson, I'd like to talk about the variance. So the variance is a way to determine how spread apart the values are of a random variable. So this number is a measure, I should say. Variance is a measure that determines, quote unquote, how spread apart. Yeah, how spread apart the values of the random variable are. So one little thing I want to say before we continue with variance is that oftentimes the expected value also known as the mean is denoted by the Greek letter mu, which is it's kind of like a U, like a script U. So we understand that the expected value is a weighted average, right, of the values of the random variable x. And we compute that expected value, and it's a number. And that number is a constant. And so oftentimes you see mu representing the mean, or in other words, the expected value of x. So this will be used interchangeably. Okay. Now, why do I say this? Well, the reason why is because the variance, so by definition, the definition of the variance of a random variable is defined as the following. The variance of the random variable x is equal to the expected value of x minus mu squared. So that's the variance. That's the way it's defined, mathematically speaking. So when we talk about how spread apart it is, the values, we're referencing the mean. We're basically saying, what are all the values of x? Subtract that with the expected value of x. So remember, this is the expected value. So you can consider this mu as the expected value of x. So we want to figure out what is the average of the difference between the values of the random variable x and the expected value of x squared. Sometimes the values of x can be smaller than the mean. Sometimes the values of the random variable could be bigger than the mean. But we're taking all those differences, we're squaring them, and we're averaging them out. And that number, so this will produce some kind of number, and that number represents the variance of x, which is how it gives us a measure as to explain how spread apart the the variables are with respect to the mean. So I should include that up here. With respect to the mean, which is the expected value. Okay. Okay. Any questions about this? Has anyone heard about variance before? So this is one definition. I'm gonna say number one, because there's another one. So let's look at this definition a bit more. So if I call variance of x, if I call this the expected value, what does this mean? How can I define this using the definition of expected value? Well, I know that this is the summation of x sub I minus mu squared times the probability of x sub I as I go from 1 through n, and n can go to infinity, right? This is the definition of the mean of expected value. And so if we consider this part here, this squared term, we can expand this, can't we? So this becomes a summation. I goes from 1 through n. This becomes x sub I squared minus 2x sub I times mu minus plus mu squared. P of x sub I. So all I did was I expanded. I took this guy and I expanded. And now when I expand this, I can also distribute. So when I distribute, I get x sub I squared times the probability of x sub I minus 2x sub I times the mu times px sub I plus u squared p sub x sub I. Okay, so all I did was I distribute. I distributed this term, so distribute. And again, this whole thing is a summation of these individual terms. Due to the nature of this expression here, I can rewrite this as a summation of x sub I squared p of x sub I minus, this becomes a summation of 2x sub I times mu times p of x sub I plus a summation mu squared p of x sub I. Everyone follow so far? So we're just applying the definition of expected value to this argument that we have inside here. This is the random variable x minus the expected value of x squared. And so I apply the definition of expected value, which is taking each of these values inside here, take each one of them, and you multiply by the probability of getting that value of x sub I. So this is what changes. This is the same. And this probability changes with respect to the value of x, which whatever that may be. I expand this It's a binomial, so we can expand it. We can distribute the probability for each of these terms. This is what I have. I have a 3 terms here being subtracted and added. And then I can reassociate them so that I'm adding all of these first, and then adding all of these, and then adding all of these. Now, what you have to keep in mind, though, is what are the constants? So if you notice, mu is a constant, right? It's a value that it's already defined. It's the expected value. 2 is also is a constant. So with that constant in a summation, I can factor that out. So I'll factor out the 2 and the mu. So I have 2 mu. I got the summation. I goes from 1 through n of x sub I, p of x sub I. Plus, and I can do the same thing here with mu squared. I can factor out the mu squared. And so I'm left with mu squared summation. I goes from 1 through n of p of x sub I. Now, what do you guys know about this summation? What does this summation here have to add up to? Any ideas? Does anybody see what I'm doing here? Looks like it's factorable. Well, again, the idea is that x, what is x? X is a random variable, correct? And what does p of x sub I represent? It represents, if you guys remember, this represents the probability that the variable x, the random variable x equals x sub I, which is some value. It's some value for x. That's why I have this little index. This is the ith value, whatever that is. And what I'm doing here is I'm adding all the probabilities for my random variable attaining the value x sub I. And I'm adding all of them up. So this actually is the sum of the probabilities for each value of x. It's the sum. So this is the PMF. This is adding up the PMF of x. But remember, for something to be considered a probability mass function, if you add all of the probabilities for every value of x, it should always equal 1. So this is going to equal 1. And then what is this here? What is this? What does this expression represent? Very good, Daisy. That's right. This is the expected value. That's the formula for the expected value. Do you guys see that? And what did we say originally? The expected value is oftentimes denoted by mu, the Greek letter mu. So I can rewrite this entire expression into a very simple letter, call it mu. So far, what do we have? We have the summation of x sub I squared, p of x sub I, minus 2 mu times mu, which would give me mu squared, plus mu squared. Do you guys see that? And now, what is this going to be? This might be a little harder to understand what this is going to represent. As you can tell, this is very similar to this expression here. The problem is that this x sub I is not squared. This is squared. What's attached to it is the probability for each of those values of x sub I. So what we call this is the expected value. This is also an expected value, but of what? This is the expected value of the random variable x squared. And then what is this? What is this here become? 2 mu squared plus mu squared is a total of minus mu squared. Right? And then again, what was mu squared? What was mu? Mu was the expected value of x. So I'm just going to rewrite that one more time. Let's write it like this. The expected value of x, parentheses squared. This is another definition. This is like the second way. Definition number 2. For variance. So the original definition for variance is given by this formula here. The variance of x is the expected value of x minus mu squared. This is the original definition. But sometimes it's a bit easier. And as you can tell, we just derived it by using the definition of expected value. Here, we expanded things out, we distributed, we created 3 different summations, we recognized, hey, some of these things we know the values of. And then we see, hey, we can actually find the variance of x as well by finding the expected value of x squared, subtract that by the expected value of x squared. So these are not the same thing, okay? This is the expected value of x, and square that. This is the expected value of x squared, which is the random variable of x, and you're squaring it. So this is another way to compute variance. Okay, so I'm just giving you the framework for what variance is and how you can compute variance. And there's one more thing that's called, I know maybe some of you have heard of this, the standard deviation. And the standard deviation is related to the variance. And the standard deviation is just another number that represents how spread apart your values are. And all it is, standard deviation also is denoted by a Greek letter called sigma, but it's the lowercase one. So this represents standard deviation, and it's simply the square root of variance. Okay, so if you know the variance of a random variable, you just have to take the square root of that number, and that gives you the standard deviation. And again, the standard deviation and the variance represent the same kind of measure. It's just that taking the square root we define it to be the standard deviation. Okay. Great. Now, suppose x is a random variable and a and b are constants. Find the expected value of ax plus b. So that's the first thing. And the second thing is to find the variance of ax plus b. Okay, so x is a random variable. So ax plus b. So one thing we have to start getting more comfortable with is not only are we given random variables, and we have to understand the probability mass function of the random variable. We have to understand how to compute the expected value of the random variable. We also have to understand that the random variables you can take a random variable and create another function based upon that random variable. The same way how we start y equals x, right? That's one function. And then we can say y equals 3x plus 2. It's another function. This is the same thing, same idea. So let's suppose I have a random variable x, and then I want to create a new one. And this new random variable is called a times the random variable x plus b. This is my new random variable. And now I want to figure out what's the expected value of this new random variable called ax plus b. And so what would be the result of me taking the expected value of this? What's going to be the result? Well, let's see. What do you think this is? What do you think I'm supposed to do here? So I want to find the expected value of ax plus b. What's the next? What can I say after this equation? It's the summation definition, correct? So a lot of mathematics, guys, I know it may not seem intuitive, right? It may not seem like I really don't know what we're even talking about here. But what I will say is that to do this mathematics at this level, you really have to base everything upon the definitions. So the definitions are like your support. They're your foundation. So if I can be like, I don't know what this is. I don't know what this is, but I do know that the expected value of anything is defined as what? It's defined as the summation. I goes from 1 to n, and again, n can go to infinity depending upon if it's a discrete random variable that has an infinite number of values. But the idea is that this here would equal this, ax of I plus b, multiplied by the probability of x of I. This is just standard. It's just a standard definition of expected value. That's all I've done. I've applied the definition for the expected value. And then what can I do here? Look at the algebra that can be applied here. What can I do? Something very similar to what we did earlier. I can distribute, and I have the summation as I goes from 1 through n of a x of I times the probability of x of I plus b times the probability of x of I. All I've done is distribute. That's all I've done. And I have to recall that what? A and B are what? A and B are constants. So you see how this is like based upon, I'm going to be applying the just rules of algebra. So from here, I can also represent this. This is a summation of this entire expression, correct? So by the associativity of addition, I can associate all of these first, the terms that look like this, and then add them to the terms that look like this. I can reassociate. So that's the idea behind the reason why I can create two summations like this. It's because addition is associative. That's the reason why. Does everyone follow this? So by associativity, of addition. And then because these are constants, I can factor out all the a's from this term, from this summation. From this summation, I can factor out all the a's, and from this summation, I can factor out all the b's. And now look what I get. I get a multiplied by the summation as I goes from 1 through n of x sub I times p of x sub I, plus take out the b, take the summation as I goes through n of p of x sub I. Now, what does this equal? And what does this equal? We talked about these earlier here. So what is this term here? What does this expression here add up to? Well, this, Alexandra, this is the expected value. That's right. This is going to be the expected value of x by definition, by the definition. But what is this going to be? You see how this is slightly different from here? We don't have an x sub I here. We just have the probabilities. We're just adding up all the probabilities. Because this is a random variable, the assumption is that when we add up all the probabilities, it's always going to equal 1. Right? The PMF, when you add them all up, it equals 1. That's the assumption that's made. So what's the result? It's A multiplied by E of x plus B. So what did we show? What did we show? We showed that expected value is something called linear. Expected value is linear. So note, expected value is linear. What does linear mean? It means this. That's what linear means. It means that if I have a summation, if I have an expected value of an expression like this, then in reality, all I really care about is the expected value of x. I multiply by a, and then I add b to it. So that's pretty important, a property, characteristic of expected value. The actual, you can think of it as a function. The function for taking the expected value is linear. And we'll see how that's applicable in other examples. So that's the expected value of ax plus b. Now, what would happen if I find the variance? So this is a new thing that we're dealing with, right? What is the variance of ax plus b? Do you think that the variance will also be a times the variance of x plus b? And I'll say that it's actually not. So the variance is a little bit different from expected value. It's not going to be a linear characteristic. But again, what is variance? We talked about variance, right? Variance has two definitions. This is the standard one. This is like the beginning. But sometimes this is a bit more complicated, convoluted to find. The expected value of this is a little bit difficult, right? But either way, it's actually good for this one to use the first definition. So what is variance? Variance of this is equal to the expected value of ax plus b minus the expected value of ax plus b. And this whole thing is squared. Do you guys see what I just did? I'm utilizing this definition here. The variance of x is equal to the expected value of parentheses x minus mu. And again, mu is the expected value of x. Okay, so I could also write it like this. So a lot of rewriting of things. I can write it like this: x minus the expected value of x. It's the same thing, okay? It's just that the mu, I replace it with the e of x, that's all. But the problem is here is I don't have x here. I have ax plus b. I have a new random variable called ax plus b. So the variance of this new random variable ax plus b is the expected value of the random variable ax plus b minus the expected value of ax plus b, all of that being squared. Now, why is this good? Why is this good? So I'm using definition 1, okay? Why is this good? Don't we know what this is? What is that? The expected value of ax plus b, isn't that exactly what we just found here? The expected value of ax plus b is a times the expected value of x plus b. Okay, so what is that going to look like? So the expected value is going to be ax plus b minus a times the expected value of x plus b. There's a lot of parentheses here. So Daisy asks, what do you mean by linear for ax plus b? Can you please explain this again? Yeah. So when I mean, or when in mathematics, when people say something is linear, if you notice, right, linear, when we talk about lines, what do you know about lines? Y equals mx plus b, right? It's a straight line. That's what you guys think geometrically speaking. But linear in mathematics is beyond just a geometric understanding of something being straight. Linear is an algebraic property. It's an algebraic property. So what I'm saying here is that the expected value has an algebraic property, which is what? It's this. And this linearity property means that if I have, for example, so one of the conditions for linearity, and I'm going to use the example of expected value, is the expected value, let's say, of if I have just x plus b like this, actually, let me write this as y. So the idea behind linearity, let me just say, let me make this a bit more simpler. A function, let me just say a function. A function is linear if the following is true. If f of x plus y is equal to f of x plus f of y. And the other property is that if you have f of c times x, this equals, and c is a constant, it's a scalar, a constant, then this is equal to c times f of x. These two things makes up what's called a linear, like this is what makes a function f linear. So these two properties, these two algebraic properties makes f a linear function. So you see here we have a sum. So the expected value, as you noticed, the expected value is linear, and because there's a summation here embedded in it. So in a sense, what you could have done here is the expected value of ax plus b is the expected value of ax plus the expected value of b. That's this linear property that I'm applying, number one. The expected value of b, if you think about it, what is the expected value of a constant? The expected value of a constant is itself b. Do you guys see that? And then so this becomes, the expected value of b becomes b. And now the question is, what is the expected value of a times x? So what's the expected value of a random variable multiplied by a constant? Well, it's very nice that expected value is the same thing as finding the expected value of x first and then multiplying by the constant a, which is this second property here. So because these two properties are applied here, expected value is quote unquote linear. Not that it's a straight line, but that it holds these two properties as true. But Daisy, that's a great question. Thank you. No, thank you for that question, because sometimes we just move on to the next thing, move on to the next thing. And that's actually very important, because this idea of linearity is not just, does not just stay here in this realm of probability. Particularly, I'm teaching also linear algebra. So in linear algebra, this idea of linearity is also very important. And you can also go into calculus about linearity with differentiation. So if you start noticing, differentiation is also linear, because if you take the derivative, if you take a derivative of a sum of functions, right? Isn't this equal to the derivative of the function plus the derivative of the other? Don't we know this? And then if we take the derivative of a constant of a function, isn't this the constant times the derivative of the function? Isn't this like the scalar multiple rule? So then what's the conclusion? Differentiation, the operator of differentiation is linear as well. We're not talking about lines particularly, but we're talking about these properties hold. So this idea of linearity is applied to a plethora of different subjects and areas in mathematics. Okay, awesome, great. So now let's continue with this variance stuff. What is the variance of ax plus b now? So I know the expected value of ax plus b is a times the expected value of x plus b. I know that. And now I want to find what's the variance of this new random variable ax plus b. So I'm applying the first definition, and I get this little messiness here. And then I realize, wait, I already computed what the expected value of ax plus b is. It's the a times the expected value of x plus b. And then I'm subtracting this whole thing. And so when I subtract, I get ax plus b minus aex plus, minus b. And this whole thing is being squared. Let me just see if this is, yeah. Now, what happens when this is squared? What happens with the b's? Don't they cancel? And then what am I left with? I'm left with ax minus a expected value of x. This entire thing is being squared. So far, I've only been using the definition of expected value. The first definition, pardon me, of variance, which deals with expected value. Then what do you notice about the two a's here? They're the same, aren't they? And this entire thing is being squared. So then I can factor out the a. But when I factor out the a, I need to remember there's an a squared because the whole thing is being squared. And what's left inside? X minus the expected value of x squared. Does everybody see what I just did? I factored out the a, which results in an a squared. But then what do we know about expectation? It's linear. What that means is if I have a constant inside, I can take that out very nicely. It's not always holds, but I can take this out nicely because it's expected value. Do you guys see that? I can take this out. And so I get a squared multiplied by the expected value of what? Of x minus the expected value of x squared. I know there's a lot of e's and x's out here. But then, hey, what is this? What is this? Anybody know what that represents? That expression represents? Well, what if I rewrite this? What does this represent? All I did here was I changed the expected value of x into mu. What does this represent? The expected value of x minus mu squared. Variance. That is right. So wait a minute. What did I just figure out? I figured out that the variance of ax plus b is equal to a squared times the variance of x. Do you see the difference in the structure or in the essence of a variance operator compared with the expected value? Expected value has very nice properties. When someone says that something has a linear property, it's very nice. Why is it nice? Because it's something that you expect. You expect that if you take the function of a sum of things, it's equal to the sum of those functions. So when you take a sum of expected value, you would assume that the expected value would be the sum of those expected values individually. But what happens in the variance world? First of all, the b disappears. In essence, the variance is not affected by adding by a constant. The constant is not going to affect how spread apart the values are. So that's another way to interpret it. If I'm just considering how spread apart values are, and I'm applying a horizontal shift by adding b to it. So every single value of x is just being summed up. So I'm moving all the values somewhere by b or subtracting by b. But the idea is that because I added by a constant, I'm not affecting the spread of those or how far apart those values are. I'm not changing that. So the variance by b, adding by b to the random variable will not affect the variance. That's another way to interpret it. But if I multiply the random variable by a constant a, oh, I did very good, Daisy. I'm glad I helped you remember some of that. That's good. So, but when I multiply the random variable ax by a, what's happening? Every value of x is being multiplied by a. And if you notice, if you go back to the definition of variance, there's a squared term. So I'm taking the values of ax and I'm squaring them for the variance. So that's why that you had this little a squared that pops up. And then you can clearly see this doesn't obey neither of the linear properties. So variance is not linear. That the moment you see something squared, it's not gonna be linear at all, because the squaring things complicates things sometimes. But does everybody see this? This is an important aspect about expected value, has linear properties, and about variance. The variance of a random variable is only affected by the constant that you multiply the random variable x by, and you square that constant. Okay, so again, we're getting more. This is a new concept of variance, and we're getting more in tune with that. And let me just say here, you can also rewrite this as sigma squared is equal to the variance. So it's just rewriting it. It's the same idea. So standard deviation is the square root of variance, or variance is the standard deviation squared. Either way, it's the same thing. Okay, any questions about variance, expected value? Okay, so we're almost there with the Poisson random variable, but I want to do one problem with expected value and variance. So let's do a more concrete example here. So if the expected value of a random variable, right? I'm telling you what it is. It's 1. And I'm giving you another quantity. The variance of x is 5. Find the following. So A is going to be the expected value of 2 plus x squared. What does this equal? And then B will be find the variance of 4 plus 3x. Okay, so it's just a made up random variable. So let's look at the first one. I know the following. They're giving me that the expected value of the random variable x that we have is 1, and the variance of this random variable x is 5. Now I have this new random variable, which is based upon the random variable x. It's 2 plus x squared. I want to find the expected value of this new random variable. So how do you think we're going to approach this? So again, if you don't have anything else to think of, you can think about, write down the definition, right? Yeah, of e to the x. We can do that, but that'll take a little bit longer. We can straight up distribute, expand. What's 2 plus x squared? Isn't this 4 plus 4x plus x squared? Right? And then can't we apply the properties of expectation, which is what? The expected value of this guy is equal to what? The expected value of 4 plus the expected value of 4x plus the expected value of x squared, correct? But what's the expected value of 4? Or if it's the constant 4, the expected value of a constant is just itself, it's 4. And then what is this going to be? The expected value of 4x is equal to what? 4 times the expected value of x. And then we have the expected value of x squared. But we know what the expected value of x is. What is the expected value of x? It's 1. So far, look what we have. We got 4 plus 4 plus the expected value of x squared. Does everybody see that? And this equals 8 plus the expected value of x squared. Now, what's the issue? The question is, what in the world is the expected value of x squared? Sure, we can try to do the summation notation xi squared times the probability of x sub I, but the problem is we don't know what the probability is. We don't know what the values of x is. All we know is that this random variable, which is randomly chosen, is that the expected value of that random variable is 1 and the variance of x is 5. So we're kind of stuck here, aren't we? What's the expected value of x squared? Does anybody have an idea of how to find this? Try variance's definition. That's a good idea. Remember, we have two definitions, right? One of them looks like this. The variance of x is equal to the expected value of x minus mu squared. That's one definition. Sometimes that works, but sometimes there's another definition that's even better. It's the expected value of x squared minus the expected value of x quantity squared. That's the variance as well. But wait a minute. I know what the variance of x is. It's 5. And the expected value of x squared, that's exactly what I'm looking for because I already know what the expected value of x is. It's 1. So guess what the expected value of x squared is? When you solve for it, you add 1 on both sides, you get 6. Do you guys see that? So I'm able to figure out the expected value of x squared if I know the variance of x and if I know the expected value of x. So I'm using this definition of the variance to figure out what expected value of x squared is. So now what do I know? This is 8 plus 6, which is 14. Make sense? So the expected value of 2 plus x squared is 14. Any questions about how I found this expected value and how I utilized my definition of variance to figure out what the expected value of x squared is? Once I'm able to do that, then I can find the expected value. And I think part B is a bit easier. That's pretty straightforward. Okay, good. I'm glad. And I think the variance of this guy should be straightforward, right? What is the variance of 4 plus 3x? Well, you can recall. What should you recall? Recall that the variance of a linear expression of x is equal to a squared times the variance of x. So this should also be a bit more straightforward, I would say, because the variance of 4 plus 3x, remember when you add by a constant, it doesn't change the variance. So the 4 is irrelevant in terms of finding the variance. What is relevant is the 3 that I'm multiplying x by. So this will equal, based upon what we just recalled, this would be equal 3 squared times the variance of x. 3 squared is 9. The variance of x was 5. So the variance of this new random variable 4 plus 3x is 45. Does that make sense? Do you see that? Okay. So those are little exercises about getting more understanding, intuition with what variance is and what expected value is, how to compute expected value of new different random variables, which are based upon the random variable that they give you. So again, this x is a random variable. So that's the nature of the game now. We're dealing with random variables and functions of those random variables. And now we have expected value and we have variance as two new functions themselves that help us understand the random variable a bit more. So we've talked about Bernoulli random variables. We talked about binomial a lot, binomial random variable. And we talked about the geometric random variable. And then the last one of the discrete random variables that we'll touch upon in detail is Poisson. Again, this is a discrete. So what is the Poisson random variable? Well, you can think of the Poisson random variable as an approximation of the binomial. So it is often considered, so I should say, this random variable is often viewed as an approximation of the binomial random variable when n is large and p is small, and making NP moderate. So this is large, whatever that means, small, whatever that means, and NP is moderate, which is based upon what N and P are. So when you have a random variable and the number of trials is really large, and the probability of success is very, very tiny, then this new random variable Poisson is a pretty good approximation to that binomial random variable. Okay. And NP, remember what NP represents. NP is the expected value or the mean or mu of the binomial random variable. Okay. Okay. And this has a lot of, the Poisson has a lot of different applications. So examples of Poisson random variables. So it is used in various different applications. You can find, for example, the number of typos on a page. That's a Poisson random variable. The number of people who survived to 100. Number of people who live up to 100 years in a community that's a Poisson random variable. Yeah, so I'm not going to give you a whole, it's a whole list, but I'm just giving you some of the examples as to see what we're speaking of here. What are the applications? The number of people entering, number of people entering a post office, for example, on a given day. Also Poisson. All right. And of course, to even speak about a random variable, you must know what? You must know its PMF. So what's the probability mass function of a Poisson random variable? If you don't have the PMF of it, it's very hard to understand what we're speaking of. So the Poisson has a very distinct PMF. So the probability that my random variable x, which is a Poisson random variable, equals I, which is some value I, and I ranges from 0 to 1 to 2. So I is something that could be 0, it could be 1, it could be 2, dot, 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 to infinity. This is similar to the geometric random variable, because the geometric random variable has an infinite number of values for the random variable. The only difference is the geometric random variable doesn't start at, the I value doesn't start at 0, it starts at 1. Because remember, the geometric random variable tells you the number of trials that it takes for your first success. So you can't have your first success in zero trials. That doesn't make sense. So that's why in the geometric random variable, you start with 1, because you can have your first success on the first try, the first success on the second try, so on and so forth. But the random variable here for Poisson is we start at 0, and then we go to infinity. So the probability that this that x equals I is given by the this formula here, e to the negative lambda times lambda raised to the ith power over the n factorial. It's a bit strange. But you can actually derive this PMF if you were to apply the PMF of why doesn't the text put it over I? Oh, pardon me. Yeah, you're right. You're right. It is. It is over I. That's right. It is over I. Yes. Yes, it is over I. That's my mistake. And yeah, this is not n, I. Pardon me. Yes. So it's I squared. And you can actually arrive at this PMF by utilizing the PMF of the binomial random variable and making some approximations with, and of course, some algebraic manipulations to that PMF. But that's the PMF. And so for any PMF, right, this must check out. What must it check out? So check if this is a real PMF. How would you check if something is a real PMF? What must be true about any PMF? If sum equals 1, right? So if I take the summation and I goes from 0 to infinity of my probability, x equals I, then this should equal what? The summation of I goes from 0 to infinity of e to the negative lambda times lambda to the ith power over I squared. But what is e to the negative lambda? And again, lambda here is a constant, okay? Lambda is a constant. Lambda. It's another Greek letter. What is this? This is a constant. I have a constant being multiplied to a whole bunch of terms in this summation. What can I do now? I can take this out, right? E to the negative lambda is multiplied by the summation as I goes from 0 to infinity of lambda to the ith power over I squared, I factorial. But then what is this? What is the summation of lambda to the ith power over I factorial? So remember, you have to remember your series from Calc 2. Does anybody recall the Taylor series? Recall Taylor series for y equals e to the x about x equals 0. Do you guys remember this? E to the x is equal to the summation of x to the I over I factorial. I goes from 1 through 0 to infinity. This is the Taylor series. So whenever you see this summation, it's a very specific structure. This is equal to e to the x. You see the same thing here, don't you? It's exactly the same. It's identical. What's the difference? The base here is not x, but lambda. But it doesn't matter. So we can write this as e to the negative lambda multiplied by e to the lambda. And what is e to the negative lambda plus e to the lambda? Is e to the 0th power, which equals 1. So it checks out. The summation works out. So this is a legit PMF. Make sense? So then can we figure out the expected value? What would be the expected value of a Poisson random variable? What do you guys think? So then how do you find the expected value of said random variable? You would use a definition. So what would be the definition? This is I from 0 to infinity of what? Of x sub I times the probability of x being x sub I. And then what is this going to be equal to? Remember x sub I, what are the values of the random variable? It goes from 0, 1, 2, 3, 4, and so on and so forth, right? All the way to infinity. So I can actually start this from equaling 1 to infinity of x sub I times the probability of x equals x sub I. Which in this case, I can just write this as the summation of I multiplied by the probability of x equaling I, because that's what the values of x are. 0, 1, 2, dot, 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 dot. But then what does this equal? What is the PMF? It's e to the negative lambda of what? E to the negative lambda of lambda to the ith power over I factorial. E to the negative lambda is a constant. You can take the e to the negative lambda out times the summation of I times lambda to the ith power over I factorial. Does anybody see what we can do now? You see we can cancel the I here. And if we cancel this I here, what's left? I minus 1 factorial. So this becomes the summation as I goes from 1 to infinity of lambda I to the over I minus 1 factorial. But then what we're going to do here is we're going to do some little algebra manipulation. I'm going to factor one of the lambdas out from the numerator. Why am I going to do that? Because look what I have now. I got lambda to the I minus 1 power over I minus 1 factorial, and I goes from 1 to infinity. I got this I minus 1 business here. So what if I call this K? What if I call K equaling to I minus 1? So then this now will be, this new expression will be lambda to the K over K factorial. And if I is equal to 1, then K is equal to 0. So I can rewrite this as K equals 0 to infinity of lambda times e to the negative lambda. But what is this? What is this, guys? The Taylor series of e to the lambda again. But e to the negative lambda times e to the lambda is e to the 0th power, which is 1. So then lambda is the expected value. So the expected value of a Poisson random variable is equal to the parameter lambda. Does this make sense? Yes. Okay, good. I just want to be able to do, I just want to do one example. I know we don't have much time, right, really. But so now that we know this, right? Suppose we have customers entering a store. Customers enter a store at an average of 1.8 per minute. And assume the number of arrivals in a minute follows a Poisson distribution So what is the probability that exactly 2 customers enter the store? So we just go over this problem here. Yeah, no problem, Rizwan, no problem. Like this literally takes less than a minute, I would say. So how do we do this? Well, we know that the average is what? 1.8 per minute. So if that's the average, remember average means mean. And remember mean means expected value. Then I know the expected value of my function, which is equal to lambda, is equal to 1.8. Do you see that? I want the probability that exactly 2 customers enter the store, which is the same thing as saying the probability that x equals 2. Utilizing the probability mass function of a Poisson random variable, this equals e to the negative lambda, which is 1.8, times 1.8 lambda to the ith power, which is 2, all over 2 factorial. That's it. So computing Poisson random variable, as long as you know the probability mass function, is not as complicated. And then you can put this in your calculator. You need to use e, right? So e to the negative 1.8 times 1.8 squared divided by 2. And I get 0.267 dot 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 dot. So this would be my probability. Yeah, it's always good to see the application of the formula, right? Because just using the formula by itself, having it there and not being used sometimes is a bit empty, right? There's no real connection to it. But that's the idea. The idea is that most of these problems are going to give you an average of something occurring. And so you have to immediately understand average, mean, lambda, that number. So lambda, again, we just showed you that lambda, that parameter, is the expected value, which represents the mean, which is the average of the Poisson distribution. So they're going to be giving you some kind of average, and then they're going to ask you for a probability for that random variable to either be 2, and then what they're going to give you is stuff like, what is the probability that it's greater than 2? So you need to find the probability, the summation of probability that when x is greater than or equal to 2. But then, of course, you're not going to find an infinite number of probabilities. That's not feasible. But what you could do is do the complementary counting, or complementary probability, which is to find a probability that it's less than 2, which is easier. And then you do 1 minus that. So that's the idea. So we're building upon what we've done in previous lectures, and it's just going to come back again. Complementary probability will come back again for these kind of problems. Yes, I will be, Alexandra. I will be in office hour today. So for those of you who need extra help, please, I'll be here at